integrated circuit 7, analog circuit, constant voltage and current source circuit. Okay, so we learn here about the famous band gap voltage reference circuit. When you have the constant voltage reference, then it's easy to make a constant current circuit too. So when you say constant voltage circuit, the constant voltage against what? Well, for the power supply voltage. So when the say 5 volt plus minus and chip operate with a certain tolerance of the supply voltage, if inside the chip, if voltage change plus minus 20%, that's problem. You can't make a chip. So inside, regardless the supply voltage, it has to be constant. And usually you can make constant from this side, but we talk about constant from the ground level. How do you achieve the constant? So that's one constant. And another is a temperature variation. When the chip temperature goes up during operation, then the constant voltage cannot shift, right? So this band gap circuit is to achieve the constant voltage, say reference 1.3 volt. This is the lowest. We can make it higher voltage, and we talk about that later. But basically what you do is we provide a current, and no matter what the current is, this voltage depends on R2, the current here R2, right? And that's depend on this. So the voltage here is VBE, which doesn't depend on this supply voltage, and this VBE3 doesn't depend on this. Okay, so basically this 1.3 volt is always 1.3 volt from here, even you change this 20% up and down. Okay, it doesn't change. But the problem is when temperature change, this voltage may change. Okay, so how do we avoid that? And the band gap circuit, this famous circuit, address that problem. How does it address that problem? Well, first of all, we reference is VBE3 plus VR2. Okay, so VBE3 is this voltage, right? And VR2 is this voltage across the R2, which is the VBE3. The voltage difference here create this voltage. This voltage divided by R3 is this one, right? This delta VBE. Sorry, this is the delta VBE. This guy, right? Okay, so V reference depends on this guy and this guy and this one. We have some current flowing for the beta. Well, this is small, so it's neglect, right? Very small factor. So from this equation, delta VBE, the delta VBE here, this guy is the difference between this. And how do we make a difference? We make a difference making Q2 large and Q1 small transistor. Okay, so what happened is the current density is higher, so this voltage across the diode is higher, this much, and this Q2 is larger and the current density is low, so Q2's VBE become this much. There is a voltage difference here, and that divided by this guy R3 determines the current, and this current is translated to R2 here, and that's the voltage here. Okay, so that's the mechanism of band gap. And right now we know V reference does not depend on V3 because it's all depend on VBE, and VBE doesn't change much when you change the V plus. Now we take a derivative of T for this one and set the 0. Try to make it the temperature dependency 0. So we get this equation. So this is a condition to compensate the V reference to be 1.3 stable over temperature. Okay, so for example, VBE dt, like, you know, it change negative 2 millivolt per degree. Okay, a typical transistor. Okay, so we set R2, R3, R2, R1 to be about this value, then temperature compensation is done. Okay, so example, here's that example. KT over Q is 26 millivolt at 300 degrees C, which is the room temperature, right? Then we have this equation. If R3 experimentally, okay, R3 is 60 ohm, quite small. R3 is this guy, small, 60 ohm. Okay, and R2, R1 is, say, we make it half, okay, to make it easy. So then R1 is the set this value, we calculate, we can make about 2 millivolt, right, with R2 1.338. So we can set R1, R2, R3 at the proper ratio, so temperature dependency becomes 0. Okay, so this is very clever design, and almost every analog IC chip use this band gap to generate the constant voltage, temperature compensated 1.3 volt. This is low voltage. In order to make it higher voltage, what you do is you stack up more diode here, and when you stack up the diode, then again this voltage is not gonna depend on this guy, because this is gonna be all the VBE dependent here. V reference is you stack up more diode and still have this term, and this time what you do is dV ref delta T equals 0. So if each one change about 2 millivolt per degree, so we have multiplied by 4, 8 millivolt per degree. So we adjust this register value to compensate this 8 millivolt per degree. So ratio is going to be changed, but we can get much higher voltage, say somewhere around the 5 volt. This is like a 12 volt plus minus, even you know, 12 volts to 24 volt, doesn't matter. You still get constant about 5 volt, you can get that. Okay, so the reason why you take it from emitter is there is plenty of supply of current through this transistor. So even you drive many circuits and each one has a current, it's okay, it doesn't affect this guy, right? So you always make it configure the output is like take it from emitter. We talk about this later too. Okay, so that's the very important band gap reference technique in the analog design, and you have to know this if you do IC chip design. Okay, so if you like this video, hit subscribe.